the next PrimaVera colloquium. We're super happy that today Sena Eruguz is talking here. So Sena has, for instance, been working a lot with Rob Buston, and this connects, of course, very well to our consortium and to the research we want to do in PrimaVera. And Sena has been an assistant professor at the Erasmus University of Rotterdam and a postdoc at Eindhoven. And now she's at VU, this is pronounced correctly, I don't know really, Vrije Universiteit Amsterdam. Her research is on operations research, in particular also on maintenance and predictive maintenance. And we are very excited to hear today's talk about maintenance optimization for multi-component systems with a single sensor. So, Sena, please go ahead.
Thank you very much, and thank you for having me here. I was actually prepared to also introduce myself, but you made a very nice introduction, Niels. Thank you very much. So I am currently working as an assistant professor at the Free University Amsterdam. I think, not better than you to pronounce a few, because I'm also not Dutch. I did my PhD in France, and I'm originally from Turkey. And before starting my position in Amsterdam at Free University Amsterdam, I worked at Erasmus, and I worked in Eindhoven as a postdoctoral researcher. And my research interests are operations research and its applications in supply chains, inventory control, maintenance, after-sales service logistics, and recently more into e-commerce logistics and sustainability. My research is mostly practice-driven. I worked in various projects in the Netherlands in collaboration with high-tech companies and also maritime companies. And today I'm going to present a research paper that relates to one of these projects. It is the Procello Next project. And the research paper's title is Integrated Optimization of Maintenance Interventions and Spare Part Selection for a Partially Observable Multi-Component System. This is a long title, but keywords are optimization, maintenance, spare parts, partially observable, and multi-component system. And this is a joint work with Dr. Oktay Karabağ from Erasmus and Rob Buston from TUE. I don't know, probably you are a bit familiar with Procello Next project, and if you are not, I would like to make a short introduction to it. It is a project on proactive service logistics for capital goods. The next steps, it is actually the follow-up of Procello project. And in this project, I got involved in the work package on predictive maintenance and service logistics. And companies involved in that work package they were Merrill, Ayse, Van der Lande, and Thales. There were, of course, other companies in Procello Next project, but these are the ones from the work package I got contributed to. And the common problem is to minimize the total cost of ownership. These companies, they are original equipment manufacturers. They are manufacturing capital goods, and for capital goods, the acquisition price is quite high. But over the lifetime of the equipment, maintenance and downtime costs, they also become very significant. And because these original equipment manufacturers, they are also getting responsible on maintenance and service logistics, they are also providing service level agreements with customers. They want to reduce maintenance and downtime costs. So this is the common starting point for all to come together and to do predictive maintenance and service logistics. And in this research paper, we got inspired from a case from the company Ayse. But we try to generalize this problem because we think it can be applicable also in other companies. And now I'm going to tell you about the the exact case that we got inspired of. Ayse is producing those industrial printers and selling those to their customers together with a service level agreement. And they promise something like 95% uptime. In these printers, there are some sensors to monitor the condition of the system. And for example, one sensor is measuring the temperature. This is the temperature measurements in a subsystem in the printer. When the temperature increases, this reflects a defect in the system. So something is going wrong in the system if temperature starts to increase. But because this system is a multi-component system, and this temperature increase can be caused by different components, we don't know exactly what happens in the system that will lead to such a defect signal. And there is probably some time before the system fails. So here we know something about the state of the system, but we don't know the exact condition of the components inside the system. And we have to make a decision to visit the customer, to either visit the customer or to do nothing. If we visit the customer, we are going to dismantle the system, inspect the system, and get a better knowledge about what happened. And then we can take some actions to replace some components. And for this, we also need to know which spare parts we have to take along. So in this problem, we have partial information. We get those sensor information. This is going to tell us something about the general state of the system, but it doesn't say what components are about to fail or which components are defective and need to be replaced. We posed ourselves the following research questions. What is the value of such an information, such a partial, compared to having full information? For example, if we have a sensor dedicated to each component, then we will have full information, and with this information, we can make better decisions. But we wanted to investigate how better these decisions will be compared to the decisions we can make with partial information. And the second question is, what is the value of an optimal policy? So if we optimize our decisions based on this partial compared to simple policies like always reacting preventively or always being corrective, what will be the value? So we investigated those two questions, and for this, we first needed to have a mathematical model for this problem. And we looked at the literature to see what has already been done, and there exists actually a quite some number of papers on partially observable systems, but these are all for single components. And these papers, they are also focusing on maintenance decisions. And recently there was a research at the Royal Netherlands Navy. I think this was a bachelor thesis from a student from Eindhoven. This student investigated how suitable a partially observable Markov decision process method will be for the components at the Royal Netherlands Navy. And the results, they were somehow promising that there exist several cases for which such a model can be applied. So the problem I described with partial information, it can be solved with a POMDP, so-called partially observable Markov decision process, and there exists a certain number of papers, but none of these papers consider a multi-component system. On the other hand, we have also quite some papers on multi-component systems, but they do not consider partial information. They consider full information, a complete knowledge about the system. So in this research paper, we bring those two aspects together, that we have a system level information. We get information from a single sensor, and this is going to give us partial information, and we want to make intervention decisions to decide when to intervene to maintain the system. By the way, if you have questions, you can ask your questions during the presentation. That will, I would like that better because my presentation can be a bit technical, and I also want to somehow balance it with your questions if I have to.
Then I have a question.
Yes, please. Thank you.
You said that there are no works, at least not in this area, about multi-component POM-DPs, right? With partial information, partial observability. In a totally different area, I think was an AI conference or something, there is actually work on, and there are several papers on so-called factored POM-DPs. Which look at the state space on a feature level, where you have really a state which is composed of certain variable values. And then there are, for instance, models called MOM-DPs, mixed observability MDPs, where some of these features, these explicit state informations, which probably in your sense are components, have partial information, others have not.
Okay.
So there are some works, but it's probably just from a completely different area than yours.
Yeah.
But you probably don't know these, right?
I didn't know this, and I will be very happy if you can send me maybe more information about that, because we specifically focused on the maintenance literature for this work.
That's what I thought, and Ayse would be very happy about your pointers there. So we can probably just exchange these and discuss a bit. Okay.
I think it will be really nice to compare those.
Yeah. Okay. Thanks.
Yeah. So I now would like to tell more about the problem definition, because I told you about the case at Ayse and with that printer, but we modeled this problem in a more general way to of course address the problem maybe at other companies that are facing a similar situation. So what we have is a system that consists of multiple components, and this system is maintained by replacing its components. The condition information is on system level. When there is a defect or failure, we do not know which components are causing it. And by a perfect inspection, meaning that by visiting the customer and dismantling the system, we can get a full knowledge about the current state of the system. So this is the setting of the problem. And in this problem, what we want to optimize is the decision of when to visit the customer and which spare parts to take along when we visit the customer. So with this partial information, we want to optimize those two types of decisions. Now I will go further into the model. I think some people in the audience, they know quite a lot about POM-DPs, so it is not going to be a problem, because we have a very classical POM-DP model here. But for an audience who is not familiar with POM-DP, I wanted to explain the model in 5 steps with those 5 different components. So what I will talk about is, first of all, the exogenous information in the system, then the state information we use to take actions, the transition function to represent the transition from one state to another, actions, so the actions to take, and finally the objective function. And let me start with exogenous information. Here in this figure, what I depict is a system with 2 components, and each component has some deterioration levels. 0 is the perfect level and F is the failed level. For the two components, the failure levels are 4 and 2, meaning that the component 1 will fail at level 4 and the component 2 will fail at level 2. So you see here the red states that will lead us to a failure signal. And we also have defect levels. When the deterioration level is at the defect level or higher, the service provider will observe a defective signal. These are the core states. These are the system states that we do not directly observe. Only by dismantling and inspecting the system, we will know the exact state of the system. So we have here 15 different core states. The green ones are the ones that will lead us to a non-defective signal. The yellow ones, they will lead to a defect signal, and the red ones, they will lead to a failure signal. And the service provider, the service provider will only be able to see those three types of signals. For the deterioration, we assume a Markovian deterioration. That is, from one state to another, we know the transition probability, and these transitions, they depend only on the current state. So we assume that we know the transition matrix for the Markovian deterioration we have in the multi-component system. So the next component is the states. And in a POMDP, in a partially observable Markov decision process, the state information is a probability distribution over the core states. So as you see in the previous slide, that we have those 15 different core states, and our state information, the state information that the service provider can use, is a probability distribution over those states. If we observe, for example, a defect signal, then we know that that the probabilities, they are at the yellow states. So for all the other states with red and green colors, the probability will be equal to 0. Then we can, this part is very classical in the POMDP. We can compute the probability of observing a certain signal in a given belief state. If we are in a state S, for example, a core state S, we know the transition probability to a core state S prime. And by doing this operation, we can obtain the probability of observing a certain signal in a given belief state. We can also compute the next state given a certain signal that we observe. So what happens in real time is that we are at a certain belief state, then we are going to observe a signal, and based on this signal, we can compute the next belief state, the belief state, the update that we have to make in the belief state in the next period. So this part is a bit technical. Sorry for if it wasn't too clear, but this is just to give you an idea about the type of things in the model and how we build a POMDP model. Then the next component are the actions. We can either decide to do nothing or to intervene, to visit the customer, to do an inspection and to maintain the system. If the signal is a failure signal, if the belief state is such that there is a failure in the system, then we have to visit the customer. And if the signal is non-defective or a defect signal, we can either do nothing or decide to visit the customer for maintenance. So we have the two options. And together with the maintenance intervention decision, we also have to decide on the set of spare parts to bring to the customer. With the current belief states, we will have an idea about the spare parts we will need in the maintenance, and those spare parts, they need to be brought to the customer. Then with this, we can build our objective function, and our objective function is the minimization of the total of the expected total discounted cost. And we consider different types of costs. If we intervene preventively, meaning that before the failure signal, we already decide to visit the customer, then this action will incur a preventive maintenance intervention cost. If we intervene correctively, then this action will incur a corrective maintenance intervention cost, and the corrective cost is typically much higher than the preventive cost, because in case of failure, the system will be down, and during the traveling time of the maintenance engineers and during the dismantling, inspection, and the maintenance of the system will remain will not be functional, and this is going to be more costly than a preventive maintenance. Then we have the cost of replacing items. When we dismantle the system and inspect the system, some components, they will be defective, and those components, they will need to be replaced. For every component we replace, a replacement cost will be incurred. Because we use spare parts, if we don't have the right spare parts to use, the spare parts will be shipped by emergency shipments, and this is also going to incur some costs. And similarly, if we brought some spare parts that we don't use at the end, these spare parts, they will need to be returned back to the warehouse, and this is going to incur a return cost. So at the end, we have fixed costs and variable costs. Fixed costs, they are the preventive and corrective costs, and they depend on the signal we observe. And the variable costs, they consist of the cost of replacement, the cost of emergency shipments, and the cost of returning parts. Here we make some assumptions about when these costs occur, because what we do here is that the emergency shipments, they will happen if the part is defective, but we didn't bring that part to the customer. And the return cost will happen if the part was not defective, but we brought that part to the customer. At the end, we will not have to replace that part, and we will have to bring it back to the warehouse. So that's how we take the different cost components into account in the objective function. Then we can build our value function. Here I'm going to skip all the details about the cost expressions. Mainly what we do in the value function is that we express the minimum expected total discounted cost using the optimal policy. And this cost, it consists of two operators, the cost of doing nothing and the cost of a maintenance intervention. In the maintenance intervention cost, all the spare part selection decisions and the costs associated with spare part selection decisions, they are embedded. So we are here minimizing the value function by always choosing the cost. The cost, we either choose doing nothing or intervening for maintenance, and we decide on what to do based on the cost of these operators. These operators, they take the immediate cost into account, but also the future cost, the cost to go when we take that action. So this was all about the model. And if you have any questions about the model, you are very welcome to ask. Otherwise, I am going to move further into the solution method we used to find an optimal solution for this problem. Let's see. Okay, then I'm going to move further to the solution method. Here we have a POMDP, and a POMDP is known to be not so, yeah, it's very computational to obtain the optimal policy. And we here implemented an approximate approach, which is a grid-based approach. And we use value iteration by using this grid-based approach. In the grid-based approach, what we do is to simplify the state space. The state information, it consists of belief states. So we have a continuous state information, and we consider a finite grid to make this state space finite. So we choose a resolution, and we only compute and record the value function on the points in the grid. Then for evaluating all other belief states, we use interpolation. And this method, it is an approximation, and it is very easy to implement, but it also has some limitations because to make it more accurate, we need to have a resolution of the grid that is very high, but then the computations, they increase. And here in this formula, I express the number of grid points we will end up with for a given resolution and for a given number of core states. So as you can see, very easily the number of grid points, so the number of computations we have to make will increase if we increase the resolution or if the number of core states gets higher. But this is a very easily implementable method, so we went for that to get some initial results, and we tested this solution method to answer our research questions. And we performed some numerical experiments. In the numerical experiments, I'm coming back to our research questions. What we want to investigate is the value of the optimal policy and the value of the information. For the value of the optimal policy, we compare the policy we find with the POMDP model with a very easy benchmark policy, which is a preventive policy. In the preventive policy, what we do is that every time there is a defect signal, we just go visit the customer and intervene for maintenance. And in the second benchmark policy, the corrective policy, we do something similar, but we only intervene in case of failure signal. So these two benchmark policies, they are very naive policies and they can be easily implemented. And we want to assess how much we will gain by implementing the optimal policy instead of these simple policies. The second question is the value of information. And for this, we compare our results with a model with full information. In case of full information, we assume that we are able to observe the current state of the system. So we observe the core states and we take the optimal action accordingly. And we compare the cost of such a system with the cost of the POMDP we implement. In the numerical experiment, we considered a simple setting, and we performed a factorial analysis to end up with a significant number of problem instances. We consider two components, and we consider a small number of failure levels. So components, they are either perfect or a level 1 or level 2 or level 3. This is so there are 4 different levels for each components. We consider different alternatives for corrective maintenance cost. Compared to preventive maintenance cost, the corrective maintenance cost can be low, can be very low, can be low, can be medium, high, or very high. And similarly, we consider different alternatives for emergency shipment costs and replacement costs. We consider different defect levels. So for the 2 components, when the defect level is 1, we get a defect signal at level 1 or higher. When the defect level is 2, we get a defect signal at level 2 or higher. And we consider different transition probabilities that we present as the reliability of the components. The components can be highly reliable, or the reliability can be fair, or they can be unreliable, meaning that the transitions they can be very sudden. And finally, we consider different correlation coefficients in components deterioration process. We consider positively correlated components. That this means that when one component starts to deteriorate, this is going to cause deterioration to the other component as well. So by considering different correlation coefficients, we are also able to represent such situations. And this is a very brief summary of the results we obtained in this numerical experiment by considering all different combinations in the setup. Here you see the relative difference of the optimal policy compared to the corrective policy and compared to the preventive policy. And we also assess the difference compared to the case with full information. So on average, when we look at all the instances compared to corrective policy, the optimal policy will decrease the costs by 15%. And compared to the preventive policy, the optimal policy will decrease the cost by 28%. And this is the situation when the correlation equals to 0, meaning that the deterioration of the components, they are independent from each other. And when you look at the different situations with different correlation values, the numbers, they do not change so much. But I'm going to tell you about what happens in the next slide. But when we look at the mean difference and also, the minimum and the maximum differences, the correlation seems like it doesn't really affect the performance of the optimal policy. And when we look at the difference compared to full information, we can say that that by having dedicated sensors for each component, we can improve the costs. We can decrease the costs by on average by 13%, for example. And the maximum is 50%. So having full information can be really beneficial in some systems. When we look at the different correlation coefficients and what happens, here in the table we report the relative differences, and the relative differences, they do not change so much. But actually, all the policies, they start to perform better when the correlation coefficient increases. The correlation coefficient, it represents how similar the components deterioration is. So actually what happens is that when the components, they start to deteriorate altogether, the performance of the all policies, they get better. And we can make the same conclusion also for the full information case, that the cost decrease of the full information, it also increases when the correlation coefficient increases. So these are the summary of the insights from numerical experiments. What we observe is that the full information, it gets very valuable if components' reliability are fairly different from each other. What we observe is that when components, they are very similar to each other or very different from each other in terms of reliability, then partial information, it is already very beneficial, because with historical data we can already make good decisions with partial information. But if the reliability of the components are fairly different from each other, then we need some more information, and then the full information case, it brings a lot of benefits. So dedicated sensor, it will bring a lot of benefits if the reliability of the components are fairly different from each other. And a second thing that we observe, which is also very interesting, is that when the components are cheap and are unreliable, then full information, it again gets very valuable. So for very expensive and very reliable components, partial information is already enough. This is a bit counterintuitive, but for cheap components and for unreliable components, we will need full information to improve the cost of performance. In terms of optimal policy, the optimal policy is valuable when the cost of preventive maintenance and corrective maintenance, they are fairly different from each other. When the ratio is close to 1, these two costs, they are too similar, and then corrective policy will be, the optimal policy will look like corrective policy, and the optimal policy that we obtain with POM-DP, it's not very valuable compared to that policy. And finally, if we have a system in which the uncertainty is very high, that is, there are a lot of core states for which we observe a defect signal, then the optimal policy gets very valuable, because the preventive maintenance policy and the corrective maintenance policy, they are in that case too simple, and they are not representing the optimal policy well enough. So these are the insights from the numerical experiments, and we believe that this is going to be helpful for the companies to make decisions on when to apply the optimal policy, or when to get more sensors to get a better knowledge about the system state. And this research can also lead to some future work. To start with, it is very easy to extend our model to a multi-component system in which there are parallel components or series parallel systems, or some structural dependencies. This can be easily incorporated by making some small changes in the model. The second direction will be to investigate some more efficient heuristics in order to deal with the curse of dimensionality. The method we applied here is a grid-based approach, and this grid-based approach is computationally very expensive. We had difficulties to solve, for example, some instances with 3 components. But with more efficient heuristics, we can get solutions also for more complex systems. And finally, this is something we currently work on. This is a work in progress, that we try to characterize the optimal policy in this in a similar problem, because in this problem, due to the structure of the decisions, we have some non-monotonic behavior in the optimal policy. So in a current work, we include the decision of whether to replace components or not. And this is an additional decision, but with this decision, we are able to solve this non-monotonicity, and we are by this we are trying to characterize the optimal policy. So this is basically it for my presentation, and I see that I took quite some time, and I am really willing to answer if there are any questions.
Yes, Sena, thanks a lot. Let me own my camera on. Yeah, this was very nice. I like this a lot. I have some questions, but let's first see if there are questions from other people.
I have a question.
Sure.
If your components would, if you would know somehow something about the failure probability of the components as a function of time, how would you incorporate that in your model, and how would that change things and in predicting when to do preventive maintenance or things like that?
As a you say a transition probability as a function of time.
Yeah, and it changes as a function of time. The failure probability. Well, in our system, in my systems that I'm dealing with, I'm dealing with systems where we do have a failure probability that increases as a function of time. Well, I find it very interesting, your talk, and I'm really thinking hard how I could use this or implement this or whatever. But one aspect that I see is that in our case we are using failure probabilities that increase as a function of time, and I thought, well, maybe you can say something about it, how you would implement that in your system.
Yeah. So what I can say is that we assume that Markovian deterioration in our model, and Markovian deterioration means that it only depends on the transitions. They only depend on the current state. But if you can define your current state such that it also takes the current time into account.
Okay.
This is, of course, from a perspective of solving the problem, it is going to become really untractable, because the number of states will explode with that.
Okay.
But if it really depends on the time, you have to at least take another dimension into account to take that part into account. I had worked for on a similar problem, but there it wasn't really the time, but it was the environment, and the environment can also be modeled in discrete as a discrete set. And then your transition probabilities, they will also depend. So your current state will also indicate in which environment you are, and then your transition probabilities, they will also depend on that. But if the thing is really the real time, then it becomes really computational, because of the number of states you will end up with this. So theoretically, it's possible. My short answer, from a modeling perspective, it's possible, but to be able to solve it, it is. It's not going to be possible with the current methods, I think.
Yeah, or I do not know enough about all this to really phrase this question in a proper way, so that you can solve it with the tools that you already have. So maybe we should simply discuss this. But then maybe Niels can also help me there. We are already working on things. So yeah.
I was also looking at Niels for that, because he has more he has more efficient methods to solve bigger problems. So and I think your question will lead us to a bigger problem.
Yeah. Well, Niels is also kind of aware of the system and the problems that we are trying to solve. So maybe he can, somewhere in the future, we can talk about this and see how we can use these methods to solve things.
And just to give a very quick comment, I mean, everything that Sena said was, of course, exactly right. You can do it in theory, but the state spaces blow up, and it all depends then on the time horizon, on the length of time intervals, so how many discrete time steps we would use. And in the end, it's, I guess, just quite worthwhile to explore it and see what can be done, because even the number of states is not always the key criterion, but also the shape of the model, how it will look like. So there are so many factors that in the end you can't always predict. And to just give a quick comment, there is also a lot of research on kind of hybrid models that combine discrete state spaces with continuous time. These are, for instance, called probabilistic timed automata. And these are, in fact, just MDPs with a continuous time component. And as long as it's just time, which just grows linearly, of course, then there are quite efficient methods for these. If it's more complicated continuous behavior, it becomes very bad. So, so this is definitely something we should and could look into. And I would be very interested.
Oh.
Yeah. Okay. Very interesting talk. Thank you very much.
Thank you.
Any other questions? So
I do have a question. So you started your talk saying you have one temperature sensor measuring a system consisting of multiple components.
Yeah.
And instead of having sensors on each of the components, but where exactly? How does that fit in the model? Because I was remembering the first slides where you had those different states, the 3.1, the 3.2, etc. And I was thinking that how is that represented in the model?
So are you referring to this?
Yes, exactly. So how do I see here from this picture the situation that you have one temperature sensor and a multiple component system?
Yeah, okay. A nice question. I think I was maybe too quick here. So it is represented here in the observations. In the observations, we simplify it into three types of observations: a non-defective, defective, and a failure observation. And how this relates to the measurements, it is basically that things, if they are on average, then there is no defect. When there is an increase, we understand that there is a defect, right? This is the defect signal. And when the system is shut down, that there is a failure. So in this measurement, there are a lot of measurements, but we simplify it into these three categories.
Okay, that's the way I should see it. Yes, that's clear.
Yeah. And this is a service provider observing these three types of failures. There's the three types of signals, sorry.
Yeah, okay.
Any more questions? So I have two. One is more high level. Let's start with that. And I mean, I ask it because I work on these problems. So we discussed before, right? And there I remember that you said you had probability problems getting the real probabilities in this model, right? So from the data derived the exact probabilities, for instance, of degeneration, failure, and so on. So what I was wondering, do you find it interesting for your kinds of models if you would say, sure, I don't have enough data to get like a reliable estimate on the probabilities, but if you could just have ranges of probabilities, which are also referred to as uncertainties, And I imagine that this often happens if you don't have like good data, you just have some indications. You can say, yeah, it's probably greater than 20%, but more I cannot say, and so on. Is this of interest for you?
Yes, of course. And this is what we try to do also in the numerical experiments, that we consider different scenarios for example, to characterize a reliable component, fairly reliable and unreliable. And this is done by looking at the lifetime, the mean time to failure, for example, or how variable it will be. But what we do is somehow this, we can construct a general idea about what a reliable component is, and then make the transition probabilities such that we approach to such a component. But as you know, we don't have real data about the transition metrics for the components. This is a very difficult data to obtain. I think this doesn't exist currently.
Yeah, and this is something we also encounter right now, right? In other problems, that it's hard to get these actual probabilities. I will, when we have our more detailed discussion, I will send you something about these. So what we do is we say, if in the model there are these intervals, just bounds on probabilities, then we want to find the optimal maintenance policy that works against all probabilities that can happen within these intervals, basically. So we call this robust. But okay.
Yes, I understand your point. Yeah. That will also help a lot, of course. We didn't use that robustness aspect, but by running the model for different instances, we also obtain different outcomes. So so in that sense, our solutions, they do not seem robust. It really depends on whether the component is reliable or not. But if you can give a range for that and then compute a robust policy for this, it's
because I mean, then you have
very interesting.
Then you have a very interesting finding, right? Because your optimal maintenance policy really depends on the probabilities of, for instance, sensor failures, right? So this is actually very nice result. Okay. The other questions are quite technical. Let's do these perhaps offline. If there's no more question, then Sena, thanks a lot for speaking here in this colloquium. This was very interesting, and I hope we can stay in touch and discuss a bit. And everybody, thanks for attending, and see you soon at the next colloquium.
Thank you very much.
Thank you, Sena.
Thank you. Thank you very much.
Thank you. Bye-bye.
Bye-bye.
Thanks. Goodbye.